Hi everyone, I'm Shauli Ravfogel from Bar University and I'll present our work on linear adversarial concept erasure. This is joint work with Twiton, Adversarial of Goldberg, and Cotterell from ETH Zurich. So we know that neural models learn rich representations of text, but can we control the content of these representations? So our goal is control the representation learning. Often we want to make sure that some concept is not encoded in the representation. For example, we might want to have word embeddings without text distinctions. We might want to have representations which are sensitive to the content, but not to the style of the text. And finally, and also the empirical focus of this work, we might want to have classifiers that do not condition on demographic attributes. So one useful use case in which we focus is the linear case, where we assume that the concept lives in some low-dimensional subspace within the representation space. I will start with some background on iterative analysis projection, or INLP, which is previous work which is relevant to our work. So INLP tries to solve this problem of removing some information, such as gender, from the representation by training a linear classifier that tries to recover the information from the representation. So we have this representation H, and we start by training a gender classifier theta that tries to predict gender, and say that here it predicts female successfully. If the classifier is able to predict gender, it relies on some set of features within the representation which are indicative of gender. We denote them in orange here. So these are all the features that the classifier uses in its decision. Now, what we do in order to remove the gender information is to remove the features that the classifier relies on. So we start with the original representation and we do some procedure I will describe shortly. And we end up with this representation, which is very similar to the original one, but no longer contains the features that the classifier has used. Now, how do we perform this operation of removing the features? What we do is projecting the representation H to the orthogonal complement of the parameter vector theta of the classifier. By that, we neutralize all the features that the classifier uses. And importantly, we do it iteratively. So we find that just performing one projection is not enough because we do not exhaustively remove all the features that are indicative of gender. So we iteratively train additional linear classifier to predict gender and iteratively project the representation to their orthogonal complement. Now, INLP works well empirically, but there are some open questions. So we want to understand whether it's optimal and how do we define optimality in this context of removing information. Does iterative projection, in a sense, optimizes some concept removal objective? And can we get the same result with less iterations? Because ideally, we want to perform the minimal intervention that removes or neutralizes the concept. In this work, we formulate an adversarial game between a projection matrix P from the set of all orthogonal projections matrices of 1K, Pk, that tries to remove the information, and a predictor theta that tries to recover it. We cast the problem in the language of generalized linear models. So we have some loss function L, we have some link function G inverse, which can be, for example, the sigmoid function in the case of logistic regression, and we have the predictor theta and the projection matrix P. Now, P tries to maximize the loss or hinder prediction, and theta tries to recover the information that P tries to remove. I would say that INLP approximates a solution to this minimax game by first solving the minimization problem by finding the best predictor theta, and then constructing the projection matrix P according to this best predictor by projecting to its orthogonal complements. More details are available on the paper. Now, we cover several special use cases of this objective, for example, linear regression, Rayleigh quotient losses, and mainly classification losses. So I'll focus on classification losses in this talk, and other details are available in the paper. So in the case of classification, we consider any classification loss. So it can be logistic loss, inch loss, etc. We will focus here on logistic loss for convenience. So in the case of logistic loss, we have this predictor theta, which tries to recover the gender information by performing logistic regression, and the projection matrix P that tries to remove the ability to perform logistic regression. Now, one problem in optimizing this minimax objective is that it's non-convex in the projection matrix P. For this reason, we perform a convex relaxation. So instead of optimizing over all the sets of orthogonal projection matrices of rank K, Pk, we optimize over the convex hull, Fk. So we define Fk to be the convex hull of all orthogonal projection matrices of rank K. So geometrically, we have this set of rank K orthogonal projection matrices, which is non-convex, and we have its convex hull. And we optimize in the convex hull to make the problem more tractable. So in training, we optimize over an arbitrary matrix P, and we perform projected gradient descent. So at each training step, we project to this convex hull. So we start with this P, and we get the closest matrix within the convex hull. Now, how do we perform this projection? So it turns out that there is a closed form formula for this operation, and we just use it. Now I will move to our experimental evaluation. We conduct experiments on BLAS embeddings and on contextual representations of short biographies annotated for both gender and profession. I will focus on the contextual representations of the biographies here, and you can find additional details in the paper. So let's start with PCA. We just perform PCA of the representations before and after our projection. So we start with the original representations, which are separated by gender. Here we see the result of our method, where we run our method with rank K or rank 4 projection matrices. So we see that all the separation has disappeared. And here we see the results of 1 iteration or 4 iterations of the previous method I mentioned, INLP. So we see that it performs less good in removing the separation by gender. Here we see on the x-axis the number of dimensions we have removed, and on the y-axis the accuracy of linear classifiers that try to recover gender. So we see that INLP needs a lot of iterations, over almost 100 iterations, in order to get to the majority accuracy in gender prediction. While with our method, RLACE, we perform very well, so we get very close to the majority accuracy after just 1 iteration. So we find a single dimensional linear subspace whose removal is enough to get to majority accuracy in gender prediction. You can find additional results and evaluation on fairness measures in the paper. We also perform some qualitative experiments on image data, where we run our minimax game on the raw pixels. So here we start with the original images, and here we see the results of enduring the ability to predict whether or not the person smiles in the image. And here we see the results on enduring the ability to predict whether or not the person has glasses. So we see that the method is indeed focusing only on the features that are relevant in removing the concept of returns. So we are performing a minimal intervention in the sense that we are only adjusting the relevant pixels for the classification of interest. So to conclude, we formally defined the problem of removing a linear concept subspace from the representation. This objective turns out to have an analytical solution in some cases, which I didn't cover here, but you can find details in the paper. And we provide a relaxation which works well in classification cases. NLP is a good heuristic for this task of identifying and removing information. And a more high-level conclusion is that it is sometimes valuable to constrain our model, right? So in our case, we constrain the adversarial intervention to be an orthogonal projection matrix of a certain rank. And by that constraint, we could have achieved tractable solutions which are not generally possible with general adversaries. So if we had some like MOP adversary, it would have been much harder to solve this problem. Thank you.